Welcome back to the deep dive. You know how the internet can feel like a fire hose of information? Today, we are taking a massive stack of sources, articles, security advisories, and threat intelligence reports, and distilling one story that didn't just make waves, it created a genuine tsunami in the world of modern web development.
We're cutting straight into the core of a security event that really changed how many organizations view their JavaScript frameworks. CVE 2025-55182. This vulnerability is so severe, it earned the nickname React2Shell, and it targets the heart of modern applications built with React server components.
That nickname, React2Shell, just suggests something horrific, right? Taking a simple declarative UI component and turning it into a remote shell, which of course means remote code execution, or RCE. And here's the initial shock factor. You needed zero authentication to pull it off.
Zero.
This flaw scored the absolute maximum, a CVSS 10.0 critical severity rating. I mean, that is the highest red alert possible.
And critically, this wasn't a flaw that required some complex setup or, some unusual developer misconfiguration. It was baked into default installations of widely used frameworks like Next.js. The moment this disclosure hit, it kicked off a security response characterized by extreme urgency because threat actors were already hitting targets globally.
Yeah. The mission for us today, for you, is to get beyond the headlines. We need to unpack React2Shell, understand the fundamental security breakdown in the core deserialization process, and then trace the chain of consequences from the deep technical issues to the organizational threat. And finally, of course, the urgent mitigation steps required to stop these advanced espionage groups and financially motivated crime syndicates alike. Okay, let's unpack this, starting with the timeline, because the speed at which this became a real-world problem is arguably just as terrifying as the vulnerability itself.
Oh, absolutely. The timeline is a textbook example of modern, high-stakes vulnerability disclosure. Lachlan Davidson reported the flaw via Meta's bug bounty program on November 29th. The development teams, including React and Next.js, they executed an incredibly rapid response, publishing fixes and the public disclosure on December 3rd. That is fast by any metric.
Incredibly fast. But the clock truly started ticking after that disclosure.
Precisely. We saw an immediate global race. Just 48 hours later, by December 5th, in the wild, exploitation was already being widely observed. Threat actors, ranging from lone security enthusiasts testing proof of concepts to organized criminal groups, had reverse-engineered the patch, developed reliable exploit code, and were actively scanning and compromising targets.
I remember checking the security advisories that week, and it genuinely felt like the entire web development community was melting down. That 48-hour window tells you everything you need to know about the value of this target.
It does, and governments recognized that urgency immediately. On December 6th, CISA, the U.S. Cybersecurity and Infrastructure Security Agency, added CVE 2025-55182 to its known exploited vulnerabilities catalog.
The KEV list.
The KEV list, exactly. And when the CISA adds something, it means federal agencies have a matter of days to patch or be taken offline. The speed of weaponization was truly unprecedented for a front-end framework vulnerability.
Let's clarify the official nomenclature, because it was initially a little confusing. We have the core CVE 55182, but we also saw another identifier floating around, CVE 2025-66478, which was Next.js specific.
That's a really important point for clarity. The Next.js specific CVE 66478 was quickly merged into the primary CVE 55182.
Okay, why?
Well, because the core root cause lay in the React server component serialization packages, not just Next.js routing logic. So the vulnerability affects any environment using those vulnerable React core libraries to process RSE data.
And that leads us to the scope of impact. This wasn't just some niche library. React server components are foundational to high-performance enterprise applications.
The breadth of exposure was huge. The core vulnerability resided in packages essential for handling the data stream for React server components: React Serverdom Webpack, React Serverdom Parcel, and React Serverdom TurboPack. If you were running specific React versions, namely 19.0.0, 19.1.0, 19.1.1, and 19.2.0, you were exposed.
And because these are foundational dependencies, the risk just cascaded across the entire ecosystem.
Absolutely. The list of effective frameworks and tools includes industry giants like Next.js, of course, but also React Router, if you're using its unstable RSC APIs Waku, at Parcel RSC, at Vite.js plugin, -RSC Hey. We're talking about the backbone of hundreds of thousands of live sites and internal applications.
What's truly critical here, and something that often gets missed in a rush to patch, is the distinction noted in the React advisory itself. It said that any application supporting React server components was potentially vulnerable, even if the application developer hadn't explicitly built or exposed a custom server function endpoint.
That is the defining feature of why this became a massive systemic threat. Frameworks like Next.js are, they're opinionated. They include the necessary backend infrastructure and routing logic to process flight protocol requests by default.
Right.
That infrastructure relies on those vulnerable core packages. So even if you, the developer, weren't actively writing server-side functions, if those vulnerable packages sat in your node modules and your server-side Node.js environment was running, the attack surface was open.
Wow.
The application was exposed not because of something the developer wrote, but because of a core trusted component included by the framework.
So it transforms the vulnerability from a coding mistake into a supply chain issue. It was a vulnerability of inclusion, not necessarily one of active implementation.
Yeah.
That makes the blast radius enormous and immediately explains why security teams had to panic.
Exactly. And the scrutiny following the discovery of this core RCE immediately revealed systemic issues in the underlying deserialization logic. This led to the rapid discovery of related or sister vulnerabilities that compounded the patching urgency.
Can you elaborate on those related CVEs? It feels like the RCE was the initial shock, but then security teams realized the whole house was on shaky ground.
That's the perfect framing. The initial RCE exposure led security researchers to probe the deserialization logic deeper, revealing several other logic flaws. First came CVE 2025-55184, a high-severity denial of service, or DOS, vulnerability, rated CVSS 7.5. An attacker could crash the server easily.
Okay, so that's bad enough.
Right. Then there was CVE 2025-55183, a medium-severity flaw, CVSS 5.3, related to source code exposure. This means attackers could potentially gain access to sensitive application source code or configuration details, which is a huge intelligence win for reconnaissance.
So information leakage and server crashes all stemming from the same logical flaw.
Yes. And the complexity didn't stop there. An incomplete patch for the DOS flaw, the 55184-1, led to the discovery of yet another DOS case, tracked as CVE 2025-67779. What this constellation of CVEs tells us is that the failure wasn't just a single line of bad code. It was a fundamental security assumption breakdown in how untrusted data was processed by the React server component pipeline. That's what elevated this from a dangerous RCE to a systemic crisis.
Right. That signals a much wider systemic issue. We've established what a catastrophic RCE, DOS, and data leakage, and the scope massive enterprise exposure. Now let's pivot and put on our engineer hats for a minute to grasp the vulnerability at its core. To truly manage this risk, you need to understand how the malicious code was executed.
Okay, we're moving into the deep technical weeds now, centered entirely on the mechanics of React Server Components, or RSC, and the flight protocol.
For our listeners who might be familiar with traditional React where everything runs in the browser, how do RSCs change the game, and what is this flight protocol?
Well, RSCs fundamentally allow React logic to run efficiently on the server, typically a Node.js runtime environment. This is fantastic for things like data fetching closer to the source, improved performance, and reducing the bundle size shipped to the client. The communication between the client, your browser, and the server where the component executes is managed by the flight protocol. Think of flight not as standard REST API calls, but as a specialized, optimized language for describing a React component tree. The server doesn't send HTML or JSON back. It sends a stream of instructions, a serialized component tree that tells the client how to render the UI, including references to other L server-side functions.
So instead of sending a fully rendered car, the server is sending the blueprints and parts list for the client to assemble the car locally.
Exactly. And the moment those blueprints, that serialized component tree, reach the server for processing, the underlying flaw is exposed. The root issue is categorized universally as CW502, deserialization of untrusted data. This is a vulnerability class that has historically caused some of the most catastrophic security failures in software, especially in ecosystems like Java, where deserialization flaws led to massive security crises years ago.
It's a classic failure of trust then, isn't it?
It absolutely is. The core issue is that vulnerable React versions failed to rigorously validate and sanitize the structure of the incoming data, which often came wrapped in chunks, typically through multi-part form data requests. The attacker simply crafted a fraudulent serialized object structure that the backend Node.js runtime accepted as valid. When React attempted to revive this structure, to deserialize it into a usable JavaScript object, the malicious code embedded within the structure was executed by the Node.js process.
So, using your blueprint analogy, the server received what looked like a legitimate blueprint request, But buried inside, disguised as a necessary component instruction, was an assembly instruction that told the system to build and execute a malicious payload instead of a benign UI element.
That's the mechanism of the RCE. Now let's get specific about the anatomy of the exploit chain, the how. Attackers needed to navigate React's internal object processing to achieve this goal.
We mentioned gadgets earlier. Can you break down what a gadget is in this context?
Yeah.
And how the attacker used properties like then and constructor to achieve RCE?
Right. So in security, a gadget is a piece of benign existing code or a specific property within an application's architecture that, when triggered in an unintended way by manipulated input, executes an action the attacker wants. Here, the attackers use the inherent structure of JavaScript object inheritance. The flight protocol uses specific references, like @$ or @$, to manage data chunks and dependencies within the serialized payload. The attacker uses these references and specific multi-part form data chunks to traverse React's internal object processing logic. They are essentially directing the deserializer along a specific path of properties.
And the critical path involved properties that exist on almost every JavaScript object.
Correct. The attacker manipulates the payload to inject values into properties that ultimately trigger a path where the Node.js runtime expects to execute a function. They leverage properties like then, which is often associated with promises and asynchronous behavior, and constructor, which is the function that creates or constructs an object instance.
I see.
A successful payload often used a chain of references, perhaps $1 then .constructor, and manipulated object data fields like formData.get. The ultimate nefarious goal is to trick the runtime into dynamically creating and executing a function via the JavaScript function constructor. The malicious value injected into the function call string would look something like require_child_process.exec shell command.
Wait, let me make sure I understand that key step for the listener. The attacker wasn't trying to hijack the main application logic. They were exploiting how JavaScript itself handles object creation and asynchronous calls. They tricked React during the process of building the component into creating a new function using their injected string and then immediately running that function via the constructor chain.
That's absolutely right. It's an exploitation of internal language features, not application code logic. And since the application is running in a Node.js environment, the attacker can leverage powerful functions like require_child_process to run operating system commands achieving RCE. This is why the vulnerability is so powerful. It moves from an application flaw to a system compromise instantaneously.
This brings us back to the crucial technical debunking that emerged during the analysis. Early reports mistakenly classify this as a classic prototype pollution attack.
Yeah.
What did the sources clarify about that distinction, and why is that important for security teams?
This is a vital point for defense. A textbook prototype pollution attack involves injecting properties into the global object.prototype, which then contaminates every object in the running environment. This often targets properties like proto. The sources, however, clarified that React2Shell is not strictly prototype pollution. While it relies on prototype manipulation, it works by traversing the prototype chain constructor, then properties that already exist on the object instance via inheritance. The exploit works perfectly fine without ever touching the global object.prototype or explicitly using the proto string.
So if your security team deployed a web application firewall rule that only blocked the string proto, they would have been completely exposed to React2Shell.
Precisely. It highlights the sophistication required to defend against these chain-based deserialization attacks. Simple signature blocking is insufficient. You need deep understanding of how the target runtime handles object revival.
Now that we know the how, let's look at the fix. Often the source code patch provides the clearest mirror image of the vulnerability. What exactly did the React team change in the code to stop this traversal?
The vulnerability was rooted in how React checked object properties during deserialization. They were using an unsafe call, value.hasOwnProperty. In JavaScript, if an attacker controls the value object, they can shadow or overwrite the hasOwnProperty method itself, injecting a malicious function. So when React called value.hasOwnProperty, it was actually executing the attacker's code.
Ah, I see.
The security fix was a classic defensive technique against prototype manipulation. The developers replaced the unsafe call with a safeguarded invocation, hasOwnProperty.call value I. Crucially, this fixed code explicitly uses a reference to the original untainted object.prototype.hasOwnProperty.
So they grabbed the original safe function from the global object prototype, stored it, and then explicitly forced the input object to use that safe function, regardless of whether the attacker had overridden its local version.
Exactly. By using .call, they ensure they are executing the known good function reference, thereby preventing the attacker from manipulating the process at that critical stage of object revival. It's a fundamental hardening of the deserialization routine to ensure integrity checks cannot be subverted.
That technical depth is crucial. Knowing that a single malicious HTTP request can exploit a deep structural flaw in object handling immediately elevates the business risk. Let's move into the consequences. Why did threat actors find this such a valuable target, and what were their objectives?
The business risk is amplified by the sheer ubiquity of React. This is the technology powering vast swaths of enterprise systems, financial portals, and internal tools. Microsoft telemetry alone showed tens of thousands of distinct devices across thousands of organizations were running the vulnerable versions. This wasn't a niche threat, it was a threat to the global digital infrastructure. Furthermore, modern organizations deploy these applications almost exclusively in containerized environments, often running on Node.js runtimes within massive cloud platforms like AWS, Azure, and GCP. While containers offer isolation, achieving RCE inside a container is often the most critical step to breaking out or, more commonly, moving laterally within the cloud environment.
The moment that 48-hour window opened, we saw a chaotic diversity of threat actors piling in. What did the sources observe in terms of the groups exploiting this flaw?
It was a digital gold rush, clearly differentiating between financially motivated crime and state-sponsored espionage.
Let's start with the financial angle. What were the monetized attacks?
The low-friction, high-volume attacks centered on resource theft. We saw widespread campaigns focused on deploying XMRig crypto miners. Sources specifically referenced Nuts and Emerald campaigns, which leveraged the RCE to execute shell commands, accessing, that downloaded and ran cryptocurrency mining scripts, silently draining server CPU cycles for profit.
Okay, so crypto mining. What else?
Beyond crypto, financially motivated actors also deployed remote access Trojans, RATs, like VShell and Etherrat, along with memory-based downloaders like Snowlight. Their goal was persistence and broader access to pivot into internal networks for ransomware or data exfiltration.
But the threat intelligence reports from Google and others highlighted the involvement of much more serious actors.
Absolutely. This is the truly alarming part. Google Threat Intelligence and AWS reporting confirmed multiple China Nexus clusters capitalizing on this RCE. These are sophisticated espionage groups, including UNC 6600, UNC 6586, UNC 6588, UNC 6603, Earth Lamia, and Jackpot Panda. These actors aren't interested in crypto mining. They are targeting intellectual property, sensitive configuration, and long-term network persistence.
The motives are fundamentally different. One group wants processing power, the other wants a permanent listening post inside critical infrastructure.
Precisely. And if we look at their tactics, techniques, and procedures, their TTP is post-exploitation, we can see the clear intent to pivot to high-value targets.
Once they achieved RCE via that single HTTP request, what was the immediate first-stage payload?
The initial payload was invariably a reverse shell, giving them interactive control. We saw the deployment of industry standards, sophisticated implants, cobalt strike beacons, and sliver implants. They also deployed custom backdoors tailored for Linux environments, such as the Minocat tunneler and the Hisonic and Compute backdoors.
And from there?
From there, persistence was key. The TTPs included modifying authorized keys to ensure remote SSH access, enabling root login, and deploying legitimate-looking, but often malicious remote monitoring and management tools like Mesh Agent to blend in with standard IT operations.
I recall the source detailing some highly advanced stealth tactics used by specific groups. It wasn't just dropping a file, it was actively trying to cover their tracks.
Yes. The evasion techniques were sophisticated. For example, the cluster known as UNC 6595 was observed masquerading the Angry Rebel Linux malware as the OpenSSH daemon and hiding it in the trusted etc. directory, trying to trick system administrators and monitoring tools.
That's clever.
Very. Furthermore, they used bind mounts, a Linux feature, to hide malicious processes and artifacts in system directories, making standard forensic analysis fail to spot the unauthorized activity. And of course, the classic anti-forensics command, history-c to clear the shell history, eliminating easy evidence of the command's run.
And how are these covert actors maintaining command and control, or CNC, especially when organizations have egress filtering in place?
They leverage legitimate cloud services to hide malicious traffic. A very frequently observed TTP was the use of attacker-controlled Cloudflare tunnel endpoints, typically recognized by the .try-cloudflare.com domain structure. This allows them to tunnel encrypted CNC traffic out of the compromised environment, bypassing network firewalls that might otherwise block direct communication to raw malicious IP addresses. It's effective, low-cost, and leverages trust in a major CDN provider.
This all leads to the most financially and strategically sensitive activity: credential and data theft. This is where the RCE and the application layer becomes a full-blown cloud incident.
That is the ultimate conclusion of this threat analysis. The RCE was merely the delivery vehicle for credential harvesting. Attackers deployed secret dismemory tools, specifically Trufflehog and GitLeaks, almost instantaneously post-exploitation. These tools are designed to scan source code history, container layers, configuration files, and environment variables for embedded secrets.
So if a developer had accidentally checked an AWS access key into an old commit in that environment, the attacker found it within minutes.
Absolutely, and the data they were targeting tells a clear story of cloud-focused lateral movement. They aggressively focused on cloud-native identity tokens and metadata endpoints. The sources highlight attempts to access common internal IP addresses, like 169.254.169.254 latest metadata, which are used by AWS, Azure, and GCP instances to dispense temporary identity tokens.
Acquiring that token allows the attacker to assume the server's cloud role, granting them access to databases, storage buckets, and other services across the organization's entire cloud account.
Exactly. The blast radius expands exponentially from a single compromised application server to the entire cloud perimeter. They also systematically targeted specific local files known to hold secrets. .os credentials, the Kubernetes configuration file, .kubeconfig, Azure Access Tokens, .azureaccesstokens.json, SSH keys, DRISA, known hosts, and even shell history files like bash history and .systory, which are often treasure troves of forgotten secrets.
Wow.
The ultimate target was not the React application, but the cloud role identity it had inherited.
That makes the lesson terrifyingly clear. An RCE vulnerability and an application running in the cloud is an instantaneous path to enterprise-wide cloud identity compromise. The threat landscape has fundamentally redefined RCE as a cloud security threat, not just a server hardening problem. Given the speed, severity, and complexity of the attack chain, let's focus now on the immediate, actionable steps organizations had to take, starting with vulnerability control, the patch itself.
The primary non-negotiable step was patching. Every compensating control is just buying time. The patch is the only true fix.
Let's detail the specific versions required for the listener. What was the absolute minimum version required to fix the RCE vulnerability in the core React packages?
To mitigate CVE 2025-55182, the RCE organizations needed to upgrade their React server component dependencies to React 19.10.1, 19.1.2, or 19.2.1, or any later version within those release lines.
Okay, but you mentioned those sister CVEs.
Right, and that's why we have to stress that patching for the RCE alone was insufficient. To address the full cluster of issues, including the DOS and source code exposure flaws, developers needed to aim for the absolute latest stable releases, specifically targeting versions like 19.2.3 or higher.
And for organizations running Next.js, which has a pretty complex versioning scheme, what was the guidance there?
Next.js handled the remediation by incorporating the fixed React dependencies into numerous minor releases. This meant organizations had to identify their current stable branch and jump forward. For example, critical patched versions included Next.js 15.0.5, 15.1.9, and 16.0.7. If you were on older branches like 14.x, the recommendation was to move to the latest patched 14.x release, such as 14.2.35. The patching effort required significant diligence across multiple release lines simultaneously.
For security teams under pressure to quickly scope the risk, what is the recommended manual assessment process if their automated scanners hadn't updated yet?
The fastest manual check involved directly inspecting the application's dependencies. Security teams needed to navigate to the project directory and specifically check the package.json and the contents of node modules. They were looking for the affected RSC packages, React Server DOM, and the Next.js versions. Validating those versions against the known vulnerable ranges 19.0 through 19.2.0 for React was the quickest way to confirm exposure, prioritizing any server component environment exposed to the internet.
Patching is the long game. What served as the indispensable immediate-term compensating control while massive patching efforts were underway.
Web application firewalls, or WAFs, became the frontline defense. Organizations were urgently directed to deploy or update WAF rules using services like Azure WAF, Google Cloud Armor, or Cloudflare to block the known exploit patterns.
So what were those rules looking for?
The WAF rules needed to be sophisticated enough to recognize the signatures of a Flight Protocol RCE attempt. The telltale signs were malicious requests containing specific HTTP headers like next action or RC action id, combined with the malicious content type, which is typically multi-part form data. Rules were designed to scrutinize payloads where these elements coexisted, blocking the ingestion structures containing the serialized object references.
Did cloud providers offer platform-level protection to ease the immediate burden?
Many did, recognizing the immediate threat to serverless infrastructure. Google Cloud, for instance, noted that for their serverless workloads, App Engine Standard, Cloud Functions, and Cloud Run, they automatically enforce platform-level WAF rules designed to mitigate the React2Shell vulnerability without customer configuration. This provided a crucial, though temporary, base layer of defense for those using managed runtime environments. But again, this was not a license to skip patching.
On the topic of external tools and rapid response, there was a major caution issued about the surge in scanning tools released immediately after disclosure. Why was that such a dangerous scenario for defenders?
This is a vital warning for any security professional listening. The rush to find and deploy proof-of-concept exploits or scanning tools created a dangerous landscape. Many initial POCs, including those shared on public platforms, were fake, non-functional, or actively malicious.
So people were downloading malware while trying to find malware?
Exactly. The danger was twofold. First, running these unverified tools could drop backdoored code onto the security team's own infrastructure. Second, and perhaps more insidious, fake scanning tools were observed harvesting API keys, cloud credentials, or the vulnerability target list from the researcher system. Security teams trying to scan their own organization were inadvertently handing over their internal network map and credentials to threat actors. Rigorous validation of any third-party tool sourced only from reputable vendors or security researchers became paramount.
That's a sobering thought. The cure turning into a new vector for infection. Finally, let's discuss threat hunting. For the systems that were compromised in that critical 48-hour window, what did organizations need to look for to detect existing intrusions?
Active threat hunting and robust endpoint monitoring were essential to identify pre-patch compromises. The most critical indicator of compromise, or IOC, to hunt for was unusual child process activity originating from the Node.js application process.
Okay, what does that mean in practice?
It means if the Node.js runtime, the parent process for the application, is suddenly observed spawning unusual child processes, that is a huge red flag indicating RCE. Specific processes to hunt for included standard shells like shipbash, cmd.exe, or PowerShell, and network download utilities like curl or regget. Node.js should not be calling a shell to download a file. That behavior is almost universally malicious.
And beyond the shell activity, what indicated the lateral movement and cloud credential theft we discussed?
Security teams needed to audit for processes accessing known sensitive locations. This included monitoring for read attempts on cloud credential files like .os credentials or .kubeconfig, SSH key files like EDSA, and any suspicious process attempting to query those internal cloud metadata IP addresses like 169.254.169.254.
So using the cloud tools you have.
Right. Cloud security tools, such as Microsoft Defender for Cloud and Google Cloud Security Explorer, provided templates to track exposed assets and map potential blast radius analysis. If RCE was confirmed, the incident response priority shifted immediately from patching the web server to isolating the cloud role identity that server was using.
But monitoring required here is incredibly deep, reflecting the severity of the threat. It's not just checking logs for errors, but tracking the internal behavior of the application's runtime.
That's the modern reality. You have to assume post-exploitation, the attacker is already pivoting to the identity layer.
Okay, let's take a moment to synthesize this critical information and put a capstone on this deep dive. So what does this all mean?
React2Shell CVE 2025-55182 confirmed the arrival of a new catastrophic threat model for modern web architecture. It represented the triple threat: maximum CVSS 10.0 severity, extreme ease of exploitation, unauthenticated RCE via a single request targeting default configurations, and the highest value target, which is cloud credentials and secrets. The root technical issue was a fundamental failure in safe deserialization logic, CWE 502, within React server components, which allowed attackers to leverage prototype inheritance traversal to execute arbitrary shell commands via the powerful Node.js runtime.
And for organizations, the defense response had to be layered and immediate. rapid patching to versions like React 19.2.3, the deployment of sophisticated DLEFs capable of blocking the specific flight protocol signatures, and rigorous threat hunting for post-exploitation implants like Cobalt Strike, or the presence of crypto miners.
But if we connect this incident to the wider future of cloud security, the most chilling lesson lies in the observed TTPs. The rapid deployment of highly targeted secret hunting tools like Trufflehog and GitLeaks post-exploitation reveals a fundamental shift in attacker priority.
The vulnerability in the application framework is simply a means to an end.
Exactly. RCE is no longer about just taking over the specific server. It's about instantaneously weaponizing the credentials and access keys found within that server environment to jump laterally across the entire cloud infrastructure. The true target is no longer the application data, but the temporary or inherited cloud role identity and access keys it holds. The next time a critical RCE drops in a cloud-native environment, defenders must assume the clock isn't ticking on their server, but on their entire cloud perimeter. You have seconds, not days, before your identity layer is weaponized.